All right, we're in lecture number 8 of the cardiovascular system, and now we get into some pretty cool stuff. And everything up till now was probably, hopefully, found to be pretty neat, but we get into some even neater stuff now. So our learning objectives are: we're going to look at the cardiac cycle. We're going to break down the cardiac cycle into systole and diastole, and we'll look at what's going on with pressures and volumes during those times. We'll identify this thing called end diastolic volume and systolic volume, and we'll talk about these phases called isovolumic contraction, isovolumic relaxation as well. So let's look at the cardiac cycle first. What do we mean by cardiac cycle? Well, let's just go with what you know, okay? So ignore the slide in front of you for now. In fact, let me take it away. So let's just go with what you know. What do you know about the heart? You know that, well, you've got the heart must contract, and when it contracts, pressure is going to go up, right? And then the heart will relax, in which case, whatever chamber is relaxing, pressure will go down. So you know that pressure and contraction are related in that sense. So again, one more time, the heart will contract, and then it'll relax, and then it'll contract, and it'll relax. Now notice I'm not being real clear about where are we talking atria or ventricles, whatever. I'm just talking in general, in the big picture. The heart will contract, and then it's got to relax. And so that contraction relaxation is the cardiac cycle. Systole is a fancy term to say the heart is contracting right now. Diastole is a fancy term to say the heart is not contracting. It is now in a state of relaxation. The myocardium is just chilling out at that point. So we go through this cycle where you go through systole, diastole, systole, diastole, systole, diastole, which is contraction, relaxation, relaxation, contraction, relaxation, contraction, relaxation. So that's what we see in the heart. But now the next thing is this. The question then becomes, well, okay, maybe that's fair. The heart contracts, relaxes, but the thing that you've ignored so far, maybe you're thinking out loud, is, again, the difference between atria and ventricles. We've addressed the fact, I think, that the atria and ventricles can't contract at the same time. Remember that delayed depolarization at that where that AV node held that wave of depolarization? That way we can see the atria contract just a bit before the ventricles start depolarizing and contracting. And so remember, that was intentional. We wanted that AV node to hold that charge just for a moment. So what that tells us then is that there is not necessarily the atria and ventricles aren't going to be completely in sync with one another. So that brings us to this slide. So we have at the top, and we have seconds over here on the x-axis, and we have a cardiac cycle that runs through in the atrium at the top, and then the ventricles down below. Now, look what's happening. The atria here is I'm going to move my cursor kind of along, 0.1, 0.2, 0.3, 0.4 seconds. I'm just going to assume as the movement of my cursor, that's kind of time ticking along. So the atria is contracting, then relaxing, then contracting, relaxing. So if you just look at that picture, I mean, you can do the math if you want to. The atria itself spends way more time where? In systole or diastole? And clearly the answer is in diastole. Because if you look at the numbers here, I spend 0.1 second in systole, and then I go from 0.1 to 0.8 for a total of 0.7 seconds in diastole. And so, again, I spend far more time in diastole than in systole. In English, what does that mean? It means that you will contract, then relax. Contract, relax. Contract, relax. And that's what the atria is doing. Well, what about the ventricles? When you look at the ventricles, what you'll see is that ventricular systole does not line up with atriosystole. Because what would that mean? In English, that would mean the atria and ventricles are contracting at the same time. And we've already established that we don't want that to occur. We need to allow time for ventricular filling, meaning for blood to dump into the ventricles. And so if they're both contracting at the same time, then both pressures are going up. We're not really effectively generating a pressure gradient. We're not really giving time for blood to move from one chamber to the other. So it makes sense that systole and the atria and systole and the ventricles are not going to line up. So what we see then, as the atria is in systole, the ventricles here are relaxing. They're relaxing so that the atria can have high pressure and the ventricle can maintain low pressure, maintaining that pressure gradient, allowing the ventricles to fill. What happens from there? Well, the atria then, when they jump into diastole, the ventricles will now jump into systole, and now they contract hard and they contract fast. Now, it's not quite as brief as atriosystole was, right? Atriosystole here, again, is 0.1 seconds. Excuse me, ventricular systole here is 0.3 seconds. So it's a little bit longer. But certainly, it contracts, and after contract, then it's going to relax again, diastole. Ventricles. I'm talking about ventricles here. So I'm going to ask the same question. Remember how a moment ago I asked you the question, does the atrium spend more time in systole or more time in diastole? And you look at the picture and you think, well, clearly I spend way more time in diastole. Same question with the ventricles. Do I spend more time in systole or diastole? And the answer is way more time in diastole. So you have this period of systole, and then you go right into diastole. So from this point in time, 0.4 to 0.8 seconds, you have both chambers in diastole. Let me say it again. From 0.4 to 0.8 seconds, you have both chambers of the heart, the atrium and the ventricles, relaxed. Neither one are contracting. What we are going to see is that the ventricles are filling during this time. Blood is going to go into the atrium and pass directly into the ventricles. But both chambers right now are in diastole. And I think that's the part that might be a little bit non-intuitive up until this point, okay? So it's not so important to me that you memorize things like 0.1 to 0.3 or 0.8 seconds. That's not so important. What's important is that you recognize that this period of systole cannot be synced up. They are not synced up between the atrium and the ventricles, and they should not ever be synced up. But it is okay for periods of diastole to overlap. Okay, this is where all chambers are relaxed. So this shows you a really nice picture. So I strongly encourage you, if that didn't make sense, pause the video right now and look at the slide and make it make sense. Okay, force yourself to make this make sense, or it is a video, so you can go ahead and rewind, of course. Okay, so this slide is just showing you, I'm showing you here, okay, here's my left atrium. This yellow is going to indicate the direction of blood movement. Here I've got that mitral valve open, right? The mitral valve opened, and now blood is moving this way. And in this period of time, if I were to ask you the question, who's got higher pressure, atrium or ventricle, it is fair to say the atrium has higher pressure than the ventricle, okay? And now this is all happening right now. It's very, very, very small, but this is all happening during this period right in time with both chambers in diastole. Now what's going to happen at the very tail end, I'm going to take the atrium and I'm going to squeeze it just a little bit. You see how I made it smaller? I made it contract. And now I still have atrial pressure higher than ventricular pressure, and blood is continuing to move from atrium into ventricle. And what I just showed you, this snapshot right over there, that snapshot is this snapshot right over here, where the atrium is in systole and the ventricles are still in diastole. What happens next? The atrium are going to relax and the ventricles are going to contract. So let's do it. Atrium now, let's get the atrium to relax. We'll open them back up. And now let's make the ventricles contract. And what are you going to see? First of all, this blood is going to stop moving. Blood is going to want to move this way, right? It's going to want to move that way. Of course it won't, because that blood will fill up the cusps of my mitral valve, and that valve will close. I'm going to leave it partly ajar just so you can see that it's closed. This is the closed position. So that blood has moved and it's pushing shut that door. Of course, the pressure gradients have also flip-flopped. Here, let me just change the arrows. And now ventricular pressure is higher than atrial pressure. Where am I right now? I'm in ventricular systole and atrial diastole. I'm right here in ventricular systole and atrial diastole. Well, what happens next? What happens next is that now my ventricle relax. I'm now going to go into ventricular diastole, and now both of these guys, the atrium and the ventricle, are now going to be in diastole, and that is this period, 0.4 to 0.8 seconds. Now, the next question then is, well, what happens to pressure gradients here? I know this isn't intuitive. I get it, but I want you to trust me that what happens is this. This pressure gradient goes back, where atrial pressure is going to be a little bit higher than ventricular pressure. That is going to allow opening of that mitral valve. That mitral valve will be open and blood will continue to fill into the ventricle. So this is the status. Atrial pressure is higher, even during diastole. Yeah, I get it. Both atrium and ventricle are in diastole right now. But right now in this window, atrial pressure is still barely higher than ventricular pressure, but is still high enough to pop open that door and allow the movement of blood in this direction. And that's happening right over here. And what are we seeing here? During this time, the ventricle is filling with blood. If you don't believe me, look at this picture here. All chambers are relaxed. Blood is moving from the atrium directly into the ventricles. All right, so that's what we're seeing here during that period of diastole in both chambers. Now, let's look at this. Thinking. Blood moves according to a pressure gradient. You know that. Blood moves according to its pressure gradient. So what we're going to do now, we're going to isolate the left ventricle. And look, the next two slides are among my favorite slides in physiology because, well, hopefully you'll like them too. So we're going to isolate the left ventricle, and we're going to start with the ventricle being relatively empty. Okay, we're going to start there. That will be our starting point. So the left ventricle is going to be relatively empty, and I'm putting it in air quotes for reasons I'll show you later. Well, I'll tell you now. That left ventricle is never truly empty, but let's say relatively empty. So what ends up happening is the left ventricle begins to fill. When does it fill? You know already. It fills during this window, right, where both chambers are in diastole. And so now the ventricle is going to start to fill, and that's what we're looking at. And then eventually it's topped off. The question is, what's the pressure at that point? In that chamber, what's the pressure? As it begins to fill, what happens to pressure? What happens to left ventricular pressure? When does the aortic valve open? Because remember, the aortic valve needs to open at some point. And then when does the mitral valve close? Well, the mitral valve needs to close in order to well, I guess it doesn't need to, but it will close. As ventricular pressure comes up, it'll close this mitral valve, and eventually the aortic valve needs to pop open to release that blood into the systemic circuit. And then the ventricle itself will then begin to empty. Why is it emptying? It's emptying because at this point now, the ventricle is in systole. So the ventricle is in systole, and it's shoving blood out through the aortic valve into the aorta. So that's happening, the ventricle begins to empty, and what happens to left ventricular pressure at that time? So again, we are isolating the left ventricle. So this is a slide that I love. If you think about this, what I would encourage you to do is pause the video right now, and I want you to map out the left ventricular pressure against left ventricular volume. And so here, I'll just start you off. I'll say at the very, very beginning, we're going to start here. We're going to say the left ventricular volume is relatively low. Left ventricular pressure is relatively low. And then what you should be able to do is you should draw out the path of one cardiac cycle. Okay, so pause the video. And I really, really mean it. Pause the video and make a good go of it and just see what happens. So hopefully that was enough pause time for you. And so if we draw this out, here's what we might do. We might say, well, okay, look, in the beginning, the left ventricle is going to start filling with blood. And as the left ventricle starts filling with blood, right, I'm moving right on the x-axis, does left ventricular pressure increase? Is this what I think happens? Is that what I think happens? Or is it something more like this, where the left ventricle fills with blood, because I'm moving to the right on the x-axis, but I don't really see any change in left ventricular pressure. So this first line here would indicate an increase in left ventricular volume with an increase in left ventricular pressure. This bottom line indicates an increase in left ventricular volume with no change in left ventricular pressure. So you got to figure that out. Say, it's got to be one of those. I wonder which one it is. So from there, let's keep drawing. And, I'm just going to pick this bottom line for now. So in fact, why don't we actually, let's delete this line right over here and continue on here. What happens next? Well, the left ventricular volume is going to be what it is, and it can only fill up so much, so that's not going to change. But now left ventricular pressure is probably going to go up as my ventricle begins to squeeze, and eventually once it hits a certain, maybe let's just say threshold, then the left ventricular volume will actually start to diminish because blood is now coming out of the left ventricle and my pressure is whatever it is. And then from here, now my left ventricular pressure is going to drop dramatically with no change in left ventricular volume. This is actually what it looks like. It's actually better looking than that. I have it on the next slide. But this pressure volume curve is, I think, really, really interesting. It's fun to think about. This is what it looks like. So we have left ventricular volume sitting right over here and at 65 milliliters. What that means is when your left ventricle is relatively empty, you've got 65 milliliters of blood in it. And then from there, I now start filling my left ventricle. And what you'll see is that as I fill my left ventricle, as I'm filling that up, when is it filling up? Again, it's filling up right here when both chambers are in diastole and at the very tail end where we see atrial systole. That's when my ventricle is filling up with blood. At the very tail end, it fills up and left ventricular pressure goes up just a wee bit. And this wee bit corresponds with atrial systole. Now, what happens from there? I've labeled these point A, B, C, D. So what happens from point B to C? If you just read the graph out, what you see is, well, left ventricular volume is now 135 milliliters. From point B to C, I see no change in left ventricular volume. I've topped it off at 135 mils, but I see an increase in left ventricular pressure from, I don't know, the neighborhood of 20 to the neighborhood of 80 or so. That's what I see. Great. No change in volume, but I see an increase in pressure. Then from C to D, what do I see? Well, I'm going to see a loss of left ventricular volume, but interestingly, At the same time that I see loss of left ventricular volume, I'm going to see an increase in left ventricular pressure. So that's what I'm seeing here, right? Pressure is going to go from 80 to, what is that? In the ballpark of, we're not quite 120 or so. But volume dropped. Volume. This is volume of blood, by the way. This is left ventricular volume of blood. So it's going to drop from 135 down to 65 because I've emptied my chamber of blood. Remember, I don't get fully emptied, which is why I still have 65 mils left. And then from there, from phase D to A, what am I seeing? I'm seeing, well, my pressure is going to drop dramatically, but I see no change in volume. Well, what does that correspond to? That corresponds to this early phase of diastole where, for a short window of time, the ventricle is going to really quickly relax into diastole, and there's not going to be net movement of blood yet because it's that short period of time where these pressure gradients are shifting over. So remember that during ventricular ejection, which is where I'm pushing blood out, I see massive, I see a higher left ventricular pressure. Blood is no longer moving. My valve is closed, something like this, right? I see a huge increase in left ventricular pressure. But in that quick moment of diastole, what ends up happening is that this thing is going to flip-flop, and it takes just a moment before I build up enough steam, so to speak, to open that door back up. So in that short window of time where blood is not flowing in while I'm waiting for that thing to, the pressure gradients to flip-flop, this is that period right over here from D to A. We're going to name these. Segment B to C, same volume during contraction. This is isovolumic contraction. D to A is isovolumic relaxation. Please take some time to walk this through. Just read the graph out on your own. Even if you can't remember words like isovolumic contraction, isovolumic relaxation, and things like that, please take some time to read this graph out on your own. Okay? The other things you should be able to answer are, where does the aortic valve open and where does the aortic valve close? And then where does the mitral valve open? And then where does the mitral valve close? And will that be at point A, point B, point C, point D? I'm not going to give it away to you. I'm going to ask you to think about that. And that'll wrap it up for this video. Describe the two parts of cardiac cycle. We did that, systole and diastole. Let's plot. We plotted left ventricular volume against pressure for one cardiac cycle. What is end diastolic volume? At the end of diastole, my volume of blood is 135 milliliters. What is end systolic volume? At the end of systole, my volume of blood is 65 milliliters. What is isovolumic contraction, also known as isovolumetric contraction? And what is isovolumetric or isovolumic relaxation? There's isovolumic contraction, there's isovolumic relaxation. Okay, now we're done with this video.